So this last problem here asks us to do the following. Set up a triple integral with bounds. And that's the pretty important part here. So we're given the following. F of x comma y comma z equals x. And w, the all-important region w, is going to be top bound, or the top, whatever caps it off on top is z equals 4 minus x squared minus y squared. And then the bottom bound, or the lower bound, is z equals x squared plus 3y squared. Okay? So what we can relabel these is the bottom one as z1 of xy, and this is z2 of xy. So here, this is all we're given. All right? So this is all the given, and as you can see, there's no explicit domain, right? We have our bounds for z, so that's going to be z can't go any lower than x squared plus 3y squared, because that's our bottom bound, and it can't go any higher than 4 minus x squared minus y squared. Okay, but other than that, we don't really have any information about d, which is determined by x and y, right? So in this case, I'll draw a diagram to show what this looks like graphically. So your professor may or may not expect you to know how to graph these things. I know I didn't when I first started taking this course, but I learned. Anyways, so what this one is, the top one, is actually called a paraboloid. Well, I think they're both paraboloids or something. I'm actually not sure. That word just sounds cool to me. So anyways, what we have is some kind of like parabola looking thing, but it makes like a bowl, kind of. So it's like going around. It's going around it's just like rotating around. It's kind of like a bowl, like I said. And the bottom bound here is an upward facing one. Something like that. Yeah, it was actually pretty good. So something like this, and then that's also like a bowl shape. Okay, so this is in 3 dimensions, and let's say it intersects here. These two intersect each other, right? So this is going to be the important point here, is the intersection between these two surfaces. So at this intersection, this disk that I just drew, right, I'll shade it in here. So this is the intersection between the two surfaces. And if we were to, like I was discussing before, I think in earlier in this video, is the projection D, or our domain. So I'll put domain is projection of W, so of our region, onto the XY plane. So I'll just say onto XY plane. Okay, I'll put plane. XY plane, which also means that domain, in this case, domain is determined by the, intersection, that's the important part, intersection of the two surfaces. Okay, where our surfaces are the given z equals blah 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 and z equals blah blah blah. Okay, so what we need to find is where do these two surfaces intersect. So this disk here, right, or whatever this shape is. Okay, and we're going to want to project it down, which means drawing straight lines down onto the XY plane. So it'll look something like that, or whatever shape it is, right? So that's what we want to do, is figure out this D down here by projecting the intersection down, straight down. So to find an intersection, you should kind of have a general idea that finding an intersection point, or intersection plane or line or whatever it is, you have to do so by setting things equal. So we're going to do so by setting these z's equal. So we'll make the left side be this, x squared plus 3y squared, okay? And so when these two are equal, that just means that our z's are equal. So the height is equal. Okay, so that would be where our surfaces intersect. And we're going to solve just to find an equation, basically, on the xy plane. So when we do this, I'm going to move some stuff over here. I'll write it over here. So then we'll get that 4 equals 2x squared plus 4y squared, right? And then if you divide by 2 on all sides, I'm just going to switch it around. X squared plus 2y squared equals 2, okay? And you might recognize this, or you might or might not, recognize this as an ellipse, okay? And I'll continue on the next slide so we have more room. So this is the equation that we got by finding the intersection. And this is an ellipse, like I said before. So let's divide by 2 on all sides here. So we get x squared over 2 plus y squared equals 1. All right. So our minor, or our major axis here, if you remember how to graph, I'll just graph it for the sake of visuals. But this is what it's going to look like. X and y. Here's 1, here's 1, here's 2. 1, 2, and 1. So we have -1, -1, -2, 1, 2, and a +1. So what this is going to look like is this on the bottom lets us know that the major axis is square root of 2, okay? Because this thing is like x over square root of 2 squared, right? So anyways, going back to graphing, so on the x-axis, it's going to stretch out, it's centered at the origin, right? And it'll stretch out all the way to negative radical 2 to positive radical 2. And then the y, the minor axis, is going to be 1. So it'll just intersect right here at +1, and then it'll go around. I'm trying my best to graph here. Okay. Alright, so something like this. So it's not a circle. This is an ellipse, like I said before. So anyways, this is what, okay, I'll resketch this real quick. Something like that, something like that. Oh, it fell off the boat there. Okay, and then something like that going down, and something like this, okay? So this is going to intersect here, right? And that being projected down onto the xy plane here, this is what we get. We're looking at this thing, okay? And that's all right in here. Okay, so this is our domain D. And we obtain that by finding the intersection and projecting it down, which kind of naturally happens. You don't have to worry, like, how do I project things? By setting the two z's equal to each other, the two equations, and getting this equation for an ellipse, that naturally happens, okay? All right. So now we're kind of almost there. We're getting there. And remember, we're just setting up the equation. We don't have to solve this all the way through. So I'm just showing you how to set it up. So from this point, what we're going to do, so I'm going to take this equation before, right? And we need to figure out a way to find out the bounds on x and the bounds on y, all right? So what I would suggest here is the bounds for x are kind of, I mean, you could use it that way if you want, like make this a vertically simple region, but then it would be like x goes from negative radical 2 to positive radical 2, and I mean, that's just, I don't like, I prefer whole numbers over radicals. So you see how y goes from -1 to 1, right? So it's going from -1 down here up to +1. So that means we have to find the bounds for x. And we can do so in terms of y as well. So let's just get x by itself. So we have x equals 2 minus 2y squared. And then to get it by itself, we have to square root. So we put our little square root sign, and then the crucial positive or minus. Okay, so what this is x equals either the negative square root, which would characterize the left side here, or the right side, which is when x is positive. So that would be the positive one. So x stays between, and I'll write it here, negative 2 minus 2y squared and positive radical 2 minus 2y squared. All right? So now we have our three bounds, and remember z was in between our z1 and our z2, and I won't write them here just because they were kind of long. I'll write it in the next step. So our remember when we're writing bounds, all of our variables have to stay within their rainbows. So that basically means I like to start with the simplest bounds on the outside. So we'll start with y, right? Because those are just constants. So we'll start with negative 1 to 1. And we have, I guess I'll give it some space. So dy on the outside. So we have our y rainbow is the very outermost one. And then we can do, now the decision is between either z's or x's, right? But remember the rule that all of the variables have to stay within their rainbows. So anyways, let's say we put z's here, and then we would get bounds that include x and y, right? Then we have z1 of xy and z2 of xy. But that's a problem because then when you plug in those bounds, we're going to get x's, and we don't have any dx's on the outside to fix it, right? So what that means is we have to do x next. So I'll put these in, and then maybe it'll make some more sense once you see it written out. Okay, that's the lower bound, and the upper bound is positive square root of the same thing. And we have dx. And our very inner one is going to be from z equals x squared plus 3y squared and 4 minus x squared minus y squared. And this is our dz, okay? And going all the way back, our f of x, y, z was just x. So that's where that came from. But as you see here, so if we look at the inner integral, we are integrating, with respect to z and holding x constant, x and y constant. But anyways, the important part here is that the bounds, see how the bounds for z include both x and y? That is fine, and that's the perfect position for the z's to be on the inside, because when we draw the rainbows for connecting the y stuff and the rainbow connecting the x stuff, right, something like that, it's all included in here. So our x and y's are included in the rainbows. All right. So and the same with x's. So then the same with y's. Sorry. So then if we look at the next set of parentheses that we would do, so this would be the second step. And then in our bounds for x, we have y's, right? And the y's, though, they are still under this rainbow or under this umbrella kind of thing. Okay? So all of the variables are included in this triple integral. So this is the right setup. Okay? All right. And then from here you would just this would be a really messy problem I'm anticipating. So that's why I only had to set it up. Okay? All right. Well, I hope that helped. And don't worry if you don't fully understand it just yet. It takes time, especially with such conceptual math. And now we're working with 3 dimensions and even 4. So it is very understandable. Just keep going and practice problems, and I'll be making there will be a problems video posted as well, where I'll do a couple problems of this sort. So good luck on homework, and I'll talk to you later.